Hello everybody! Thank you for attending our Innovate to Grow presentation. This is our final design review for delivering the optimal location of solar panels for our client, BART. We are Team 6 and my name is Sydney Washington. I'm a 5th year mechanical engineer and this project's communication officer.
My name is Carlin Coleman. I am a 5th year environmental engineering major, and my role for this project was coordinator and event planner.
Hello everyone, my name is Dan Leal. I'm a 5th year mechanical engineering major and I am the task officer.
Hi, my name is Ricardo Marquina. I'm a 5th year engineer and I was a record keeper for this project for BART.
Throughout this presentation, we will be walking through the steps it took to come up with a solar panel system like the one on the left of the screen. We will be running through the design, the problem, and the solution that we came up with, the performance of the system, the different components that make up the system, how we tested the system and analyzed the risks, discussing the testing and various variables. We will run through the economic analysis, which is considering the initial investments, depreciation, and revenue. Then we will run through the environmental analysis, considering the positive and negative impacts of our project, the ethical considerations, and our recommendations. Lastly, acknowledgements, and we will have time for questions at the end. So who is BART? BART is the Bay Area Rapid Transit System spanning from San Francisco, San Mateo, Alameda, Contra Costa, and Santa Clara. Their vision is to support a sustainable and prosperous Bay Area by connecting communities with seamless mobility. Their mission is to provide safe, reliable, clean, quality transit service for their riders. They opened back in 1972, and today they have a goal to run off of 100% renewable electricity by the year 2045, and we would like to help them reach that goal. So our problem is that we need to provide a combined energy output enough to power location and electric vehicle chargers. The constraints that we have is that it has to be efficient and capture the maximum amount of sunlight. It has to be safe and accessible for maintenance and daily activity, has to be manufactured in the United States, and it has to withstand environmental issues such as weather, shading, and things of that matter. Some negotiable constraints or things that we can work with is the arrangement of the solar panels for the power output, the type of inverter that we will use for our project, the storage, meaning the power grid or the batteries and things like that, and then the amount of space that the product will span. Our objective is to generate maximum power for maintenance facility and EV chargers. It has to have low environmental and safety risk, and it will be maximum efficiency throughout the lifespan, which is about 25 years. Also, it has to be cost-effective American solar panel system.
Our design solution is a fixed standard ground-mounted solar panel system at the Antioch Maintenance Facility on Sunset Drive. What we first did to come to this solution is went on NRO National Solar Radiation Database to find the maintenance facilities that receive a lot of solar radiation. From there, we used Google Earth Pro to look at those maintenance facilities and found the ones with minimal to no shading. Through this process, we were able to find Antioch Maintenance Facility as an optimal location to place solar panels. We wanted to place our solar panels at a maintenance yard to not lower revenue cost at a station and allow for other commercial projects to go on at the stations. This location has minimal to no shading and allows for an adequate DC system size as there is a lot of space to work with to place the system. A fixed standard ground mount system was chosen as it will be placed on the land which is not currently being used and will not interfere with day-to-day activities, as there are many cranes and trucks passing by, so another system like a solar carport would not be feasible. There's also better maintenance accessibility as the solar panels will be easier to clean since they are on the ground. The picture to the left is where the solar panel will be placed, which is about 338 feet by 110 feet. Moving on to the design performance. Our solar panel system consists of 720 solar panels in total, which is 60 modules in a 15 by 4 arrangement, which would be 337.6 feet by 109.5 feet. One module is 12 solar panels in parallel, which is 80.4 feet by 3.5 feet, as shown in the pictures to the left. The modules and rows are connected in series, and the modules and columns are connected in parallel. By using this arrangement, our system has a direct current DC system size of 343 kilowatts. This DC system size gives us a system output of 573,716 kilowatt hour per year, according to NRail's PV watts calculator. Antioch Maintenance Center uses around 565,000 kilowatt hour per year, so our system is able to produce just as much, if not a little more, of power than Antioch uses, thus allowing BART to run the Antioch maintenance facility on almost 100% renewable energy.
Now we have our component overview, which outlines the inflow and outflows of a solar panel system. Of course, first we have our solar panel, which collects energy from the sun. This is done through the photovoltaic or PV cells, and metal conductive plates take the electrons from the photovoltaic cells and send the electricity to the wires. Of course, we have our cords and cables of the system, which transfer energy and data between all the components of the solar system. And our junction box connects each solar panel to the one next to it. It keeps power flowing in one direction and prevents it from feeding back to the panels. After the solar panel, the energy from the sun is sent to an inverter, and then the inverter collects that energy and allows it for our daily use. Additionally, we have our battery pack, which takes excess energy from the converter and stores it for future use. The solar panels we decided to go for were the Mission Solar Panel 385 watts. These solar panels have a dimension of 78.7 inches by 39.68 inches by 1.58 inches and contain 72 photovoltaic cells. They weigh 52 pounds and have an efficiency rating of 19.11%. This efficiency rating is on the higher end for solar panels, as the average efficiency rating for solar panels ranges between 15 to 20%. These solar panels have a rated voltage of 40.84 volts and a rated current of 9.426 amps. They can function between the temperature range of negative 40 degrees Fahrenheit to 185 degrees Fahrenheit. These solar panels are also BAA compliant for government projects. As we mentioned in previous slides, it is required that BART uses solar panels that are manufactured within the U.S. Mission Solar is headquartered in San Antonio, Texas, and their modules are produced there. Lastly, these solar panels cost $260 per panel. Now to go on to our specific components of our selected solar panel. We have our anodized aluminum alloy frame. This protects internal components and provides structure to the solar panel. There's our 0.126 inch tempered glass. It has low iron and is anti-reflective. The glass protects PV cells from external factors and is safer than standard glass when shattered because it is tempered. Also, we have our ethylene vinyl acetate, also known as EVA encapsulant. The encapsulant provides adhesion between the solar cells, the top surface, and the rear surface of the PV module. Additionally, the encapsulant also prevents moisture and dirt from entering into the components of the solar panel. Our selected solar panel also contains P-type monocrystalline silicon photovoltaic PV cells, which convert the sun's energy directly into electricity. Additionally, there is the polymeric laminate backsheet. It protects the inner components of the module, specifically the photovoltaic cells and electrical components. The backsheet also acts as an electrical insulator. Lastly is our junction box. It houses the wires connections in order to split off power from a single source and into multiple outlets. The junction box also connects two solar panels that are next to each other together. The purpose of a microinverter is to convert direct current energy generated from solar panels into usable alternating current electricity. The microinverter we decided to go with was the Enphase IQ7A microinverter. It has a max input DC voltage of 58 volts and a max input DC current of 15 amps. They cost $187 per unit and are used for 295 to 460 watt solar panels with 60 to 72 cells. This is ideal, of course, for our solar panel because our solar panel is 385 watts with 72 photovoltaic cells. Lastly, we decided to implement a battery into our solar system so that no energy would be wasted and some energy could be stored to be used during a time when the sun isn't available. So as a reminder, the purpose of a battery is to store energy for later consumption. and is charged by a connected solar system. This stored electricity is used after sundown, during energy demand peaks, or a power outage. We chose to go with the humless universal 10.4 battery backup system. It can be used on and off the grid and has a max input DC voltage of 58 volts. Similar to our microinverter, this is used for 200 to 95 to 460 watt solar panels with 60 to 72 cells.
For our testing analysis, we identified the important factors that would impact the efficiency of our system. We wanted to ensure the solar panels are absorbing as close to maximum sunlight that they could absorb. Factors that we tested was the angle, the direction, and the arrangement. We determined that the solar panels needed to be at a 25-degree angle facing south, with the modules and columns in parallel and the rows in series. This way we would get the optimum voltage and amperage output. Other varying factors that we could not control was the weather and the potential induced degradation of our project. For example, we will use the image on the left to demonstrate our testing method. Before a solar panel system like this is installed, the angle, the direction, and the connections need to be specified. A system like this may have gotten the maximum amount of sunlight at a 45-degree angle. The direction may have needed to be opposite of the mountains because the mountains prevent some sunlight. And the solar panels then require a series or parallel connection to get the maximum amount of current and voltage flowing through the system. With the longitude and latitude of our system, we were able to use the PV Watts calculator to calculate the best system output of kilowatt hours per year. We then ran calculations for the voltage and current produced by the array with different series and parallel arrangements to figure out which one would provide the maximum amount of power output. Then we ensured that the energy is not overproduced without proper energy storage.
And now for the risk analysis, we made sure the diesel tanks were at least 25 feet away from the solar panels, but in this case they're 28 feet, which gives at least 3 feet of clearance, which is it's not the best, but it's good. And then another thing to take into consideration, make sure the workers have proper training, use the proper equipment, and always have their PPEs on. Another thing is we would like to gate the system off so only authorized personnel can enter, and this will help avoid vandalism. Another thing to take in consideration is electrocution, so make sure they use DC disconnect switches, so make sure they turn it off before you trying to alter or fix something. Use proper wires and insulated tools. Ensure proper lockout and the components, and make sure the components are not live. To avoid system component failure, we ensure that the panels can resist extreme temperature, solar exposure, and humidity. And to test them daily, use an amp tester to make sure they're outputting the sufficient energy that's needed to power the plant. And now for the economic analysis, we take into consideration everything, which is labor, the total parts, and all the components that takes to build the whole system in the designated area that we have. It comes out to $427,355, which is not that bad of a cost, because if they install by 2021, they get a tax incentive of 22%, which then deducts everything to coming out to $333,336 with 90 cents, which is pretty darn good for the amount of output energy the solar panels are going to put out. And the first year revenue is $82,160 with 32 cents, but each year after that, then the value goes up because of inflation. But after the 5 years, everything starts paying off, and it takes into consideration maintenance fees, inflation rates, and revenue into account. So after year 6 plus 10% of incentive from the state, they're gonna get nothing but good revenue out of this system. So it's a great investment. So now we take in consideration the environmental analysis, which we take into consideration the land that we're using and the negative effects and the positive effects that comes to installing these solar panels. And one of the negative effects is land will degrade over time. It's like a habitat loss because it weakens plants slash roots and predisposes them to invaders and pests. And another thing is the use of land. It comes with a negative effect in a way that it cannot be used for parking no more or transportation, because since the solar panels are mounted to the ground, now you can you can't do anything else with the land. That's just for the solar panels. And one of the things to take into consideration is when the workers are cleaning the PV cells, they have to use chemicals to clean them and make sure they're using proper PPE so nothing bad happens on their skin, bad skin reaction or something. But besides the negatives, this comes with plenty positives. It lowers the carbon dioxide emitted by such as natural gas and coal. It lowers it. And another great thing about it that it helps BART reach 100% renewable energy by 2045, which is a great thing.
The engineering code of ethics is really important to us. Because of this, the area of the solar panels will need to be remeasured in person, as the measurements were taken in Google Earth Pro, so there might be some slight variations. What needs to happen is the measurements in Google Earth Pro need to be compared to those measured in person, as we do not want to provide a system that does not work in the given area. The design also needs to be reviewed by a professional engineer, as we are not licensed professional engineers. Furthermore, instructions and safety precautions must be followed. If not, there could be electrocution risks, fire hazards, and workers may get hurt. Finally, our design does not pose any intentional threat to health, safety, and the well-being of the community. Any actual threats that may happen are if the solar panels are damaged, as they may leak some chemicals, or during the cleaning process of the solar panels, as the chemicals may leach to the ground. However, the cleaning supplies are approved by the government. As for our recommendations, we recommend installing the solar panel system next year in 2021, as there is a 22% tax incentive. If the system is installed in 2022, there will be only a 10% tax incentive, and after that, it is unknown if Congress will bring back the tax incentives. As mentioned before, we highly recommend that a professional engineer review the designs and approve the projects, as dimensions need to be remeasured in person, and we are not licensed professional engineers. We then recommend to purchase all recommended components for installation. After the solar panels are installed, they should be cleaned and maintained every 6 months or as needed in order for the solar panels to continue operating at around its peak performance. In addition to that, an amp meter should be used with maintenance to ensure that the solar panels are having the expected power output. We recommend the solar batteries be replaced every 10 years or as needed. For the microinverters and solar panels, they are expected to last around 25 years, and we recommend that after the solar panel's lifetime is up, that they are recycled. Thank you for choosing to attend our presentation. Right now, we would like to go through some acknowledgements. Thank you to everyone who made Innovate to Grow possible. Thank you to BART for helping us throughout and for giving us this opportunity. And also thank you to UC Merced faculty for guiding us along the way and also for giving us this opportunity. We really appreciate you all. And again, thank you all for coming. And with that, are there any questions?